Hello and welcome back. In this video we'll start chapter 10 with looking at some correlation, and in particular we're going to be looking at linear correlation. So this is something that we had discussed before. Linear correlation, correlation is just when values of a variable are associated to another variable. There's all sorts of kinds of correlation, and correlation could mean that when one variable is going up, the other one is going up. What correlation could mean when one variable is going up, the other one is going down, and that relationship between them could be linear. So, for instance, linear correlation is when we have correlation between the values, and the plotted pairs of points form a straight line. There are other sorts of correlation. There could be exponential, there could be quadratic, there could be all sorts of different kinds. We're going to focus on linear correlation. So when we look at some sort of scatter plots where we have some associated x and y variables, we can see that sometimes we get something that looks rather like a straight line, and that line could be pointing up, it could be pointing down. But we see that here's pretty clear that our points form roughly a straight line. For this third one down here, maybe it's a little bit less obvious. It still looks a little bit more spread out, so it's maybe not as linearly correlated. So what we'll do in this section in particular, we'll be looking at, okay, even though we can see that this roughly has a linear correlation, maybe it's less strong. Maybe it's a weaker correlation here. So we'll be able to assign a number to basically say this number means that these are going to be linearly correlated. Whereas this last one over here doesn't look like it's linearly correlated at all. There's no line that I could draw through it to roughly describe the data. One thing that we'll have to be careful of is that we can have data that is correlated. So here, this data looks like it comes up, it comes down. So there really is this pattern to this data, and it's pretty clear that the data follows this pattern. So this is not linearly correlated because this doesn't form a straight line. However, the techniques that I'm about to show you for calculating linear correlation, you can still calculate the linear correlation numbers associated to this. They're just not going to mean very much. Even if you can find that a number that describes how linearly correlated this is, we can see visually that this does not form a straight line. So there is some subjection, some subjective inference that we'll have to use here. Like, can we see that things are linearly correlated? Sometimes it will be fairly obvious. Sometimes it's not quite as obvious, but it still looks like it. Other times it will be clearly not linearly correlated. So the number that we will use to describe linear correlation is R, and it's called the linear correlation coefficient. And this measures the strength of the linear correlation between paired values. So when we look at these, we see that x and y are going to be paired. So for each x value, we have one y value. For each value of x, we have a value of y, and we can look to see whether or not it forms a straight line. R is going to describe how strong that linear how linear it is, and R will take values somewhere between -1 and 1. R could be exactly 1, R could be exactly -1, or any number in between. And these have different meanings. So when R is close to 1, it means that we do have a linear relationship. And when it's close to 1, it means that linear relationship is positive, meaning that the line is going up. If R is close to -1, this also means linear, but it means that our line is going to be going down instead. 0, when R is close to 0, means that it's not linear, and we don't have a linear relationship, a linear correlation between the two variables. So when we want things to be linear, what we want to find is a number that's either close to 1 or close to -1. The closer it is to 0, the less linear it looks. A couple of things. R doesn't change with scale. So for example, if we were comparing body height and weight, the taller you are, usually the more you weigh. But if we instead worked with, instead of pounds, we worked with kilograms, or we worked with any other units, or instead of say like inches and feet, we work with meters and centimeters. R isn't going to change when we change scales. So for instance, you could double all of your x values, or take all of your y values and cut them in half. R, whether or not it's linear, doesn't change. So this is quite nice. It doesn't matter the units that you're using as long as they're all the same units. Also, swapping x and y does not change R. So if we think about it, for instance, height and weight are going to be fairly linearly correlated. But if we switch to thinking about weight and height, they should also be linearly correlated. It shouldn't matter if we're looking at linear correlation between x and y or y and x. So swapping those values won't change anything. And then it's important to be able to correctly interpret what R is. So R is measuring the strength of a linear relationship. So if we start with something that's not linear, R doesn't mean anything. So a good first thing to do whenever you're looking at data and you want to measure the linear correlation, plot it. Does it look like a line? Then you can calculate R and it'll mean something. If it doesn't look like a straight line, R really isn't going to mean much. It's not going to tell you the strength of the association between x and y. It's going to tell you how linear it looks. So this is something that you have to look at it and see a linear relationship before you want to calculate R. And the last thing is that R is very, very sensitive to outliers. So the presence of an outlier can make some linear data look very nonlinear. The presence of an outlier can make nonlinear data look linear. So R will change a lot depending on if there are outliers. So it's very important to keep in mind 4 and 5 here. We want to look to see, does the data just look visually, just like in our subjective mind, does it look like a line? And does it have any outliers? And those are two things that we really need to keep in mind if we are going to look at R. So just some notation. Really, the only important ones are these top ones. So we'll say that x and y are going to be our paired data values. So we'll have x will be one variable and it'll have some values. Y will be some variable it'll have values, and they are paired. So each x is associated to a y value. N is just going to be our sample size. These are the most important ones. R is our sample correlation coefficient. This is the number that we're going to look at and say, this seems pretty close to 1. It seems linear. Or maybe it seems close to 0, and it doesn't seem very linear. Rho, the Greek letter rho, which is R in English, is the population correlation coefficient. So R is just going to be the sample in the same way that x bar is the sample mean and mu is the population mean. So we have our population. The last 3 here are just looking at the formula for R involves some summations. So for instance, the sum of x, we just add up all the x values. So sum of x squared, we square all of our values and then add them up. Notice that if we add up all the values and then square them, these guys are different. So if you square the x values and then add them up, versus if you add up all the x values and then square it, those will give you very different numbers. So let's look at the requirements here. So again, like I kind of mentioned before, so 2 and 3, 2 is just a visual, plot the scatter plot, see if it looks linear. If it's not linear, then we shouldn't be calculating r, because r isn't going to mean much. And then number 3, r is again very, very sensitive to outliers. So again, sort of subjectively, if we do see outliers, we should ask ourselves, are those outliers truly outliers? Are they just part of the data set? Or did they come from measuring errors? If we're comparing heights and weights of people and looking to see if there's a linear correlation, and then you get to someone who's, let's say, 1,000 inches tall, that's probably not an outlier. That's probably someone wrote down the height wrong. So again, it's just important to look for outliers. They may exist. There's nothing we can do about them. But if they come from errors, we should delete them. And then the last one, our samples, just like everything else, have to be simple random samples. We can't collect them from clustering or anything like this. So ultimately, there's a formula for R, for our linear correlation coefficient. It is this big monstrosity. This is not something that you will have to memorize, but you should look at it and go, this is something that you could calculate given a long time, but this is something that you could calculate. Multiply all the x's and y's, add them up. Add up all the x's, add up all the y's. Square all of the x values and add them up. Add up all the x values and square them. All this is just multiplying and adding some numbers with a couple of square roots. So this is something that you could do, but the computer will do it for us. This formula is a little bit easier to understand. Maybe a little bit harder to compute than this top one if we were doing it by hand. But essentially, it's just multiplying all of the z-scores for the x values and all the y values. We add them up and divide by n minus 1. And I won't really go into where this comes from, but this is a little bit easier to see than this top one. So what I want to do is I want to follow this up with just going through StatCrunch and calculating R for some data values. So we want to find R for the following data. The textbook gave this example, but they didn't give units, which is frustrating. So I think this is looking at countries, and it's how much chocolate the country will eat versus how many Nobel laureates, how many Nobel Prize winners has the country had. So the question is, are these correlated? Are these linearly correlated? Well, we can graph that. There's only 5 points here, but we can graph that, and it looks fairly linear. It looks like it could be coming up like that. So, okay, maybe it's reasonably linear. It doesn't look like there's too big of outliers here. So if we come to StatCrunch, we can see that I have input all the data here. This first one was the chocolate, and these were the number of Nobel laureates. So if we come to stats, we can go down to summary stats. We want to summarize the data, and we can calculate the correlation between these two values. So we need to select the columns that we want, both the chocolate and the Nobel. I'm not going to do any of the options here, but I will just compute, and it comes up with a number for us. That number is 0.79, if we could, and then we can round it to 5. So that's pretty close to 1, which indicates that there is a linear relationship here. However, it is probably unlikely that consuming more chocolate causes more Nobel Prize winners.